Okay, so let's talk about the assignment from yesterday on that angular motion thing. So, again, you have to look at, and this is one of the first things you really have to understand, is that when is radius a factor and when is radius not a factor. So, if I look at this wheel as this goes around, does every point on the wheel have the same angular velocity? Chuck? You got a
Angular velocity?
50-50 shot. Yes. Angular velocity.
On
Does
every
every
point of the
point
wheel?
on the wheel have the same angular velocity?
No.
Reevaluate that answer, Chuck.
Yes.
Because to determine angular velocity, does every point on that wheel make one revolution?
Yes.
Does every point on that wheel take the same amount of time to make one revolution?
Yes.
So if you look at omega equaling theta over time, every point on this wheel goes through one revolution in a certain amount of time. So angular velocity at any point on the wheel is going to be the same. So if you look on that question on number 4, what's the angular velocity of the Earth as it spins on its axis? That should be a really small number. So as our rock spins, okay, every point on the Earth travels through 2 pi radians in 24 hours. So no matter, that's why I didn't have to give you the radius of the Earth to do number 4. Okay? Now, linear velocity, sometimes referred to as tangential velocity, that's going to be V equals R omega. That is dependent upon the radius. Okay? So this is why when you look at when we launch satellites or anything into space, we want to do that very close to the equator, because at the equator is when you have your greatest tangential velocity. So that gives you a boost trying to get things launched into orbit, because you're launching from something that's already spinning very quickly. Very, very difficult to get something into orbit when you launch from like close to the North or South Pole, because you don't have very, very much tangential velocity created by the spinning of the Earth. So to launch from the North or South Pole takes much bigger engines because of the fact that you have to get that going faster because you don't have that initial speed from the spinning of the Earth. So, your answer to number 6, because it's asking from the distance from Joe, should be around 1, okay? Something like that. Every answer on 7, 8, and 9 should start with a 1. Okay? Every answer on 7, 8, and 9 should start with a 1. Okay? Now, when you get to number 10, let's say that you get to number 10 and you go, man, I don't have the faintest idea how to even start this problem. I don't know what's going on. So this is just a suggestion. Sometimes this helps kids out.
This is how you explain it, right?
Rework number 10, but put it in terms of like linear motion. And you would say, oh, wheel starts at rest, it's accelerated at 5 meters per second squared. How long will it take to move through 12 meters? What's the final velocity? So if you're struggling to figure out how it's playing out with angular, put it in linear and then see if that makes sense. Now, but no matter what, Connor M., what am I going to have to do with those 12 revolutions in problem number 10? To get that into radians, okay? So 10 kind of builds off of each other. So that first answer on time on number 10 should be between 4 and 6 seconds. Okay? So that first time on 4 and 6 should be between 4 and 6 seconds. So if you're struggling with that, let me give you a hint. Alpha equals 1, or theta equals 1/2 alpha t squared plus, but not time, which is nothing more than x equals 1/2 at squared plus v naught time. They're just rewriting it in terms of angular motion. On the problem out of the book,
I got a different for each.
on 3A, you should have 2 answers for each one of those. You should have a plus, minus, plus, plus, something like that on all of those on A, B, C, and D. If you just have like just one, a plus or a minus, I don't know which one you're talking about because you have to give velocity and acceleration. So make sure on 3A, B, C, and D that you have 2 columns, okay? A plus and a minus and a plus, something like that, okay? Anything else on that? Going once, going twice? So, Alex,
Number 5 is quite an interesting one in terms of how are we going to define direction?
on which one? On the one that I gave?
Question number 5 from the book.
It's just how fast you're going. You don't have to give it a direction. It's just how fast are they moving? Out of the book?
I got like
Yeah, from the book.
9, 8,
5 questions are
9.
applied to a door as seen from above and figure.
And again, counterclockwise is positive, clockwise. That's why I tell you the directions, how it's defined.
So we're going to assume the same affair.
Yes. Yes. Okay. Andrew, stop that camera for a second.